Well, good morning, everyone, and welcome to the Fiber Broadband Association's Fiber for Breakfast. We're now on our fourth episode of 2024, and I'm very excited. Today's the fifth episode of our Quantum series, sponsored by Cubatech, to educate our audience on the amazing advancements in quantum technology and quantum networking, made possible by fiber broadband networks. But before we kick off, I'd like to thank Wesco, the platinum sponsor for Fiber the Breakfast, and I'd also like to thank Cubatech for sponsoring the Quantum series. Hey, great news in Washington. The government was able to avoid a shutdown last week with Congress passing a bill that President Biden signed into law on Friday to fund the government to stay open until March 8th. In this light, Congress is going to be debating spending over the next month. So now is the time to advocate for additional funding for the Affordable Connectivity Program, which we'd like to call ACP. The FCC's ACP program is at risk of running out of money by April. There are over 22 million American families that are currently depending on ACP to be able to afford to have access to high-speed broadband service. The FCC has asked Congress for $7 billion to fund the program until the end of the year, but the FCC has begun the wind-down process on the program with the lack of this funding. So enrollment for new ACP recipients ends on February 7th, and the program is scheduled to end completely on April 8th if new funding is not appropriated. One way to advocate will be participate in our Don't Disconnect Us Day, which is happening tomorrow, January 25th. 1 in 6 households in the U.S. will be notified that the Affordability Connectivity Program is ending, and the Affordability Broadband Campaign plans to take action with encouraging everyone who cares about affordable internet to contact a representative and tell them to fund the program before it's too late. FBA will be sharing more details on how to engage tomorrow morning on our social media platforms. Our first regional Fiber Connect workshop is coming up on February 8th in Richmond. We have an amazing lineup of speakers, including Joey Winder from Treasury with $10 billion on the Capital Projects Fund, and our former FCC chair, Ajit Pai. Registration for Richmond's open, but not for long, as we are very close to being sold out. But you can go to register for Richmond by going to richmond.fbaevent.org. And we have, in addition to Richmond, we'll be in Little Rock in April, Park City in June, Des Moines in September, Albuquerque in November, and then our big annual event, Fiber Connect 2024, will be in Nashville, July 28th to 31st. Also, this morning, after Fiber for Breakfast, please join us at 11 a.m. Eastern for our webinar to present the results of our first fiber deployment cost survey with our research partner from Cartesians. So you can go to our fiberbroadband.org/event and be able to register. So you're not going to want to miss that. That brings us today's Fiber for Breakfast session with Coleman Collins of IonQ Quantum Business Solutions, who's going to be discussing hybrid quantum computing. Before I formally introduce today's guest, I'd like to introduce David Norris from the team, who's going to walk us through some housekeeping items.
Thank you very much, Gary. And before we do go over those logistics, I'd just like to once again thank Wesco, our Fiber for Breakfast Platinum sponsor, and Cubatech, the sponsor for this Quantum series. So thank you again. And to everybody who's joined us today, all participants are in listen-only mode. To ask a question, please type it into the question box located within your control panel on the side of your screen. We will also be hosting a Q&A session near the end, so we'll be able to address those questions then. This presentation is being recorded and will be available on FBA's website within 24 to 48 hours. You can find the recording in the Events tab under the Fiber for Breakfast drop-down option. Finally, at the conclusion of the presentation, you'll be prompted to complete a brief feedback survey. Please take a moment to do so. We appreciate your input. And now I will pass it back over to Gary to once again introduce our panelists and get us started.
Thanks, David, and good morning. I'm Gary Bolton, the President and CEO of the Fiber Broadband Association. Last week on Fiber for Breakfast, our guest was Joey Winder, the Director of Treasury's $10 billion Capital Projects Fund, who spoke on making a down payment on the administration's goal of affordable, reliable, high-speed internet for all. It's a great session, so if you missed it, you can watch the replay, or you can come to Richmond and see him live in person. Today on Fiber for Breakfast, our guest is Coleman Collins of IonQ Quantum Business Solutions, who's going to be discussing hybrid quantum computing. Coleman currently serves as Director of Product Management at IonQ and has been with the company for the past 6 years and graduated from Notre Dame University. So welcome, Coleman. And for our audience, please type in your questions as we go, and we'll work them into the Q&A at the end. With that, I'll turn things over to Coleman.
Thank you. I'm going to be that guy for 1 second, just in case there are any other Notre Dame grads in the room. University of Notre Dame. It goes at the beginning. People are very particular about that. It's not important to this talk, though. This talk's about quantum computing. So I work at IonQ. The front matter of these slides, the first probably 5 or 6, are just some things about IonQ. I think we can probably zip through them pretty quickly because, well, all of this is on the website and we only have so much time. IonQ makes quantum hardware. We additionally, we make them specifically using what's called the trapped ion technology. This is a picture of our latest generation machine, which is called Forte Enterprise. If you click one more, there's some details about it. We are racing as quickly as we can towards this promised land called commercial quantum advantage, or production quantum computing, which basically means the time, which is not quite here, but is very, very close, where businesses will be able to use quantum computers to solve business problems in a production context. We'll get to some details and some prognostication later, but that is what IonQ is trying to do. We're trying to do it in 2 main ways. One is building the best hardware in the market, and the other is building, if you click to the next slide, a stack of offerings on top of that let us engage with our ecosystem partners who are just doing algorithm application development, just doing consulting services, just building software platforms and middleware. We believe in an ecosystem strategy and supporting our partners throughout the entire stack, as well as actually playing in the space a little bit ourselves, mostly because it lets us understand what our customers need and want, but also because it helps us actually do the thing that we're really good at, which is sell compute time on these leading quantum computers. We're up to, I think, our 7th total generation and 3rd, soon to be 4th production generation of quantum computers at this point. We're at 35 AQ algorithmic qubits, which is a measurement of basically, so when you think about quantum computing, you think about the utility of quantum computers, you need to think about not just quantum computing size, how many qubits you have, but also how good they are. And AQ algorithmic qubits is our sort of single number metric to try and summarize that, to say, you know, we have 35 qubits and we think they are all useful in an algorithm, which means you can actually use them. Kind of the big thing that we're fighting against in quantum computing right now is this hardware noise. We're trying to get to things like error correction, error mitigation to fix these. So let's move on from what IonQ is. And I, for the record, basically run product for all of our stuff that isn't the box itself. So we have a different product management director actually does the physical hardware, and I do all the software that runs in the box, as well as all of the software that runs in the cloud to actually support remote access, shared access, all of our business models. So why quantum computing? It's worth touching on this briefly because I do think it's important and is the reason I work here. So quantum computing has the potential to dramatically change almost everything about the way we think about solving problems with computers. And this is a very, if you go to the next slide, this is, it's a little hard to prognosticate how exactly quantum computing in a production era will impact the world, because it's kind of asking, like, what will computers be good for in 1955? We don't know yet. We have a lot of good ideas as to what will be the earliest capabilities that'll come online. These are in optimization, machine learning, chemistry is probably a little later, but not too far. Obviously, code breaking is one that people talk about all the time. But in the long term, this is really just a new kind of computer that does a different kind of math. And that different kind of math is really beneficial for certain kinds of problems, especially in modeling the physical world. So, you know, everyone who has a team that's working on photonic modeling and optical modeling, quantum computers will almost certainly be able to help with things like that. All sorts of complex multi-science optimization, manufacturing, as well as a bunch of machine learning tasks. If you go to the next slide, this is actually an example of a bunch of things that we're working on with customers right now as kind of pilot applications that we think will come online kind of early in the era of quantum computing. So chemistry, quite a bit of machine learning type stuff around object detection, image generation and detection. We can do anomaly detection, predictive maintenance, optimization problems that then could be applied to any number of things. We're currently working on one with Airbus for cargo loading. You can use this to model and manage and optimize financial data portfolios, as well as do interesting risk management tasks. Quantum computers can be used as sort of a what's called the generative adversarial network, a GAN, which is an AI technique to produce lookalike data that will help financial models and financial modelers train to better predict future black swans than they can right now. So it's really exciting. It's a really exciting field to be in. To be clear, right now, no one is trading quantum compute time for bottom or top line in their business. There's a lot of value in quantum computing in doing this R&D, understanding the problem space, understanding when your use case will come online, but we're not quite there yet. IonQ is quite bullish on this. We think that we're 2, maybe 3 hardware generations from this this meaningful moment, and that will come very, very fast, especially in the timeline of business and government spending. So that's why we care about quantum computing. What is hybrid quantum computing specifically? What does it matter? So I think the important thing to realize here, the important thing to know here is that people hear about quantum computing and they think, okay, what's going to happen to my current world, my infrastructure, all of the fiber that we've laid down, all of the classical computers that we invested in? And the answer is realistically nothing. Quantum computers will be an amazing addition to the existing infrastructure and network and compute that we have. They will not be a total replacement. Unless you specifically are in the business of making, I don't know, tailored ASIC chips for specific types of problems, it's unlikely that your market will be dramatically disrupted by quantum computing directly. Now, it will unlock the capability to do all sorts of problem solving that you can't do right now, but that doesn't mean, if you go through to the next slide, that doesn't mean that quantum computing will be able to solve every problem, and it won't be able to replace classical computing. We won't want it to replace classical computing in a lot of the things that we do right now. If you go to the next slide, this is sort of our metaphor for this that we like. You wouldn't take an airplane to the grocery store, right? Like, there are purpose-built tools, and a quantum computer, if you really want to boil it down, and this is the next slide, is really just a sort of a new kind of a coprocessor in the same way that an ASIC is, or a GPU or a TPU is. It has some slightly different requirements. It has some really interesting networking needs in the long term. But fundamentally, 100% of these applications I'm talking about will still require a quantum computer and a classical computer working together in harmony. So the sort of application layer will still be classical, and then we'll be running. We don't have the right metaphors for this yet because we're still working on the programming models and the software, but running, to use kind of a GPU metaphor, we'll be running quantum kernels and quantum threads inside of that, that then have your specific coprocessor, your specific problem solving for your optimization, for your chemistry problem, whatever. But it's still working in the context of a larger application that will look much like it does today. There's quite a lot of software and hardware development to get there, which I'll talk about in a second, but that's where we are. And that's kind of the nut of hybrid quantum computing. If you go to the next slide, this is kind of how we think about it at a really high level. You've got this hybrid application. We hope and intend that as the software tools improve, and we are working on improving these software tools ourselves as well, that you'll be able to basically treat this like in the same way you can kind of multiprocessing and hybrid processing. Right now, I've got some piece of my program, a solver, that I can do GPU acceleration on. Well, now I can do QPU acceleration on it too. And at the level of that end user, it should be relatively abstract in the long term. In the near term, it still requires quite a bit of kind of custom hand-rolled expertise, but that's the thing we're trying to build towards a better future on. And then below that, you have your hybrid runtime. This is actually where you're starting to integrate quantum and classical. And you have your hybrid control system, which is basically the quantum computer itself. Even the quantum computer itself is, in a sense, a hybrid quantum classical system, because we are running these circuits. We are then pulling off individual, what we call mid-circuit measurements. We are doing something with those, and we're using that to generate new quantum instructions. And that's critical to our future of error correction. It's critical to all sorts of interesting data loading strategies. So classical computing is still super necessary in quantum computing. And the really interesting and hard question is actually this one, which is how do we make them work together better? Because right now it's a very sort of hand-rolled, you have to know a lot about both systems to make it work. Again, to use the metaphor, it's much like trying to program for a GPU in, when was NVIDIA founded? Like 1992, right? We still have a lot to do to actually make it so you can just spin up a workload somewhere, deploy the quantum resources and make that happen. But that's the future we're going towards. Next slide. This is a quick diagrammatic example of what I'm talking about, where, and you can set up the infrastructure for this right now. It's very brittle and sort of custom. You can't have a more general purpose platform that does this quite yet. You have your commercial application, then you have some kernel solver inside of it that has a decision engine that says, do I want to run this on a GPU, a CPU, a tensor processing unit, a custom ASIC, or is this an appropriate use case for a quantum computer? If it is, then I'll spin up this quantum kernel, which is running in this kind of quantum runtime. And where that quantum runtime is an interesting question, because again, right now, it's a little bit far away from the computer itself physically, like it's on a box in that room or in the cloud nearby. And as we mature this hybrid conversation, that gets closer to the system, that makes it more performant. You have higher data throughput, you have faster latencies. And then again, even inside of the QPU, you have this kind of hybrid loop of being able to monitor and measure and kind of fiddle with the actual quantum information you're working on with, again, classical systems. And so that's, you have these different layers of hybrid that are all happening at the same time that we have to orchestrate. If you go to the next slide, I already spoke to this a little bit, and I know I'm running short on time, and I want to leave time for questions. So I'll only cover this briefly. But basically, this is how we're thinking about how hybrid quantum computing is maturing and will mature, which is really just the story of how quantum computing is going to mature as we integrate it more successfully and tightly into production applications for whatever use case you might have. And again, those use cases won't all come online at the same time, and the earliest ones are probably a few years away, but this will happen quite fast, and the gains will be, I think, disproportionately given to the early movers. So right now we have this thing called remote hybrid, where I'm talking about this runtime, this application, that's somewhere else, that's in the cloud. It could be in sort of a co-located data center, but there's not a lot of benefit aside from latency from doing that right now, because those integrations and those workflow tools are not really there yet. It's loosely coupled, it's mostly proof of concept, it's mostly research. If you have an R&D arm at your organization, they should be thinking about this right now, but it's on a payoff timeline of, like I said, 2, 3, 5 years, depending on your application. Soon we're working on pushing these parts of the runtime down the stack, as we call it. Some of them will be in the QPU itself, some will be in these co-located spaces, but you're still kind of in this loosely coupled hybrid world. And then in the very long term, 4 or 5 years, what we want to get to is what we're calling kind of quantum accelerated HPC or scaled hybrid, where you have these deeply interconnected quantum and classical systems where you can have a whole GPU cluster, a whole like HPC cluster with this, whatever the InfiniBand of quantum ends up being, this high-speed backplane that will let us actually do these really meaningful kind of complex workloads, both because then you have this much better data throughput, but also because you can start parallelizing these workloads in the same way that I can send a thread to, a box that has 8 GPUs in it. So when we think about interconnected quantum computers in that same way. And then even also, and this kind of touches on some of the quantum internet stuff that I know Qubitekk is really interested in driving forward, you can start pulling in quantum data sources, quantum sensors, doing whatever you might have into those calculations when you have this sort of scaled, more robust world, and then being able to actually operate on that quantum data with a quantum system, as opposed to moving into the classical world, then coming back, which actually is a very lossy process. You end up being able to do some really interesting things in modeling and talking about the physical world. This will have, I think, probably immense implications in geoengineering, in oil and gas, as well as in many defense applications. And so that's sort of the the quick and kind of fiber for breakfast version of what hybrid computing is and how we're thinking about it. And it's really just, it's the same story as hybrid computing generally. We're just talking about how are we going to make quantum computers just as easy to use, just as integrated as your GPU clusters are today. And this, to be clear, is a bit of a long road. Like, this isn't going to happen overnight, but it's going to happen sooner than you think. I really do believe this only a few years away from these early quantum advantage applications. And when that happens, we will see a Cambrian explosion, and the acceleration will only get faster from there. If you go through to the last slide with text on it, which is, there's a bumper and then one more. I know it's early. I know this is sort of a quick talk, so I just wanted to leave you with a few points to, I know coming to these sessions is as much about educating yourself and making yourself smarter as also having your talking points to say, hey, I went to this thing and it was interesting and here's what I learned from it. So I'll give you them straight so you have them. Commercial advantage is not here yet, but it's coming very soon. No one is using a quantum computer to solve a business problem today, but we believe we are just a few hardware generations, a few years away from this moment, and it will be an immense moment because the things we can unlock here are really amazing in the optimization space, machine learning, chemistry, and a million other applications. And we don't even know all of the applications yet because we're just looking at these very early ones, because that's the only that's as far as we can see right now. Quantum computers, that said, are not good at everything. They're specialized co-processors that only provide advantages over classical in some specific areas. The way I like to think about this, you take away all kind of the scary esoteric quantum piece of it, it's just a different kind of coprocessor that does a different kind of math really well. And that different kind of math is only applicable to certain problems, at least in the sense of creating really meaningful speed ups. Now, these problems that we know are all trillion-dollar industries, right? Optimization for logistics, materials modeling, chemistry, pharma, finance, but it's not for everything. And that means that all production quantum computing will be what we call hybrid. It will rely heavily on classical compute to manage the applications, manage the runtimes, be able to work with classical HPC systems and more. And most critically, it takes an ecosystem. There is no way we as IonQ can do this alone, right? We are one of the largest and most established independent, independent companies working on this problem today. In addition to, many major tech conglomerates have quantum arms, and there are many other startups that are smaller than us, and they're all going to be critical in this success story, right? And that includes people who are working on networking and fiber. And so we're excited to work with all of our partners to kind of bring this future to fruition. And with that, what questions do we have?
Hey, Coleman, thanks. So when we think about Moore's law, and as we get more and more transistors and cut costs, right, every 18 months, we're getting down to atomic level. And so that this is the extension of Moore's law that now we give, I'll call it a quantum leap into, quantum co-processing and so forth. Is that the way we want to look at this?
Yeah, that's one very useful way to look at it. So there's two pieces of that. One is that, and this is a whole other topic, but people do think that there is going to be eventually we're going to run into a scaling problem with classical systems. Moore's law can't continue forever. It can probably continue for a little while yet. And A, yes, quantum computing will be able to pick up where that takes off. But B, there are certain kinds of problems. And again, RSA, this code breaking thing, is the classic example everyone uses, that even if you had a computer the size of Earth, like the number of bits as atoms in Earth, you would not be able to solve a meaningful ground energy state estimation on a caffeine molecule. You would not be able to break RSA 2048 with a classical computer because it's just the wrong kind of math. And quantum computing and quantum algorithms have certain access to these other sort of mathematical tricks, these other ways to model and solve problems that will actually let us unlock not just things that we can't with classical computers today, but we won't ever be able to unlock with classical computers. So it's a yes and answer. And
so when I think about what quantum applications, I think of iterative processes, anything that's trial and error. So whether it's, curing cancer or coming up with better ways to develop batteries or anything that you're doing trial and error, versus a straightforward computation, what you do with classical computing?
That's not strictly true, although many of the earliest applications that come online are going to be these iterative processes. Yeah, you're optimizing over some field to try and find the optimum binding energy of a molecule to bind with some protein, or doing a graph problem to try and route trucks or what have you. But there are other applications that are a little bit farther out that are kind of much more one-shot, solve through the maze of possibilities in a new way. But yes, that's right. Many applications look like that. And that's also why kind of hybrid is important, because that back and forth is managed by a classical computer.
So, okay, so we talked about hybrid quantum computing. So how does this play in the quantum internet?
It's a great question. So in a couple of ways. One is that as part of the scaling story, we will want to be able to connect physical quantum computers with each other, with then also a classical backplane, such that they can actually understand, like, there's some meta information that you need to be able to network these systems together. So you need the quantum internet to actually send the coherent information, which is coherent is a sort of domain term that means like still quantum information, the quantum information, and then also classical information to be able to understand your timing regime, understand kind of which photons and ions are entangled, and then actually be able to operate on these systems as large contiguous systems, or be able to pass entangled pairs around for key distribution, things like that. So I think it's all part of the same story. In the same way, we will need kind of hybrid solutions to the quantum internet too. It won't just be all quantum information moving around. It'll also be classical information that supports that quantum information.
So you mentioned a little bit about trapped ions. So why trapped ions? Why is that better for the quantum internet?
Yeah, so basically it's because we use our basic unit of operation is an ion. And the way we actually address our ions, we don't, unlike, for example, a superconducting system where you have loops of wire and then all of your control plane is actually also wired in physically with, I think it's actually gold, not copper. With ions, we use lasers, which is to say we're already sensitive to visible. Actually, there's a big technical move in our business. We're moving from an ion species, ytterbium, which is an element, to barium, which is a different element, specifically so we're closer to a fiber optical wavelength, because we actually have the ability to do photon-ion interactions already. It's already what we do. And so being able to then do that across longer distances, so rather than inside of one kind of ion chain or ion trap, across different systems is much, much easier. Still, to be clear, a relatively hard engineering problem, but much, much easier than having to up-convert that signal from a microwave regime to an optical regime, then send it somewhere, and then do the reverse and still have that information stay coherent.
All right, let me just end with, okay, so you kind of said we're a few years away. So when are we going to see production quantum, and kind of what's the first application going to be?
I mean, that is quite literally the billion-dollar question. If I had a crystal ball, I'd love to know myself. I think I will say that in the kind of 6 years I've been at IonQ, we've moved from an if to a when question. And I think the when question is really about how soon we can find these early applications that only require sort of smaller, more limited quantum computers. And kind of our engineering organization and our technical leadership really strongly believe that'll be our system that we're calling Tempo, which has around 64 algorithmic qubits and is scheduled for, I think, production release, early access maybe next year, and production release in 2026. We think that will, if not actually unlock commercial advantage, bring us to a point where people will be able to find the first commercial advantage applications and then run them probably on the Harper generation after that. And this is just my own prognostication. I'd be very surprised if we leave the decade without early quantum advantage.
Well, Coleman, thanks for sharing all your expertise and knowledge with us, get us a little bit more familiar with hybrid quantum computing. So thanks for that. And I want to thank everybody for joining us and look forward to getting back together next Wednesday. We'll be speaking with Jim Stegman, the CEO of CostQuest, to discuss the critical role of the broadband fabric and precision data for funding programs. So as you know, CostQuest is the genius behind the newest, latest, and greatest FCC maps. So it'll be good to see what's behind the covers. Thanks, everyone. We'll see you guys next Wednesday, and hopefully see you guys in 30 minutes for the we'll review the results of our first annual fiber deployment cost study. So please join us for that. Thanks, everyone.
Thanks, Gary. Thanks for having me.